I'm going to discuss question 11 for my CPR credit. If we have two charges Q and QT and the vector pointing from Q to QT is R, the force that QT experiences according to Coulomb's law will be this expression. Now let's divide the Coulomb's law by QT. We can notice that the QT on the right hand side will cancel, leaving us with FQT divided by QT, which is the expression of the electric field intensity of the point charge Q. In this diagram, we can see that the vector points from QK to QT is R minus RK, and below is the expression of the force acting on QT due to QK. Since superposition holds with Coulomb's law, we can sum all the forces that act on QT. We can find the electric field intensities caused by multiple point charges by dividing the expression we obtained by QT, since electric field intensities is defined with Coulomb's law, so superposition holds also for electric field intensity. Now I'm going to talk about the energy and potential in an electric field. In this electric field, suppose I want to move Q from position A to B along the dotted line. We can see this movement as a combination of these little dl. The work that's being done through this dl is minus Q times E dotted dl. If we want to find the work that's being done from A to B, we need to integrate the expression from A to B. Potential is the amount of work that's being done to move 1 coulomb of charge. Therefore, the potential difference between B and A will be the work divided by Q, or negative the integral of E dotted dl from A to B. If we want to find the potential field of a point charge, we can plug the expression of the electric field intensity of a point charge we acquired earlier into the equation of the potential difference. The unit vector in the r direction dotted with differential length will become the differential in the r direction. The distance from the point charge to A is RA, and the distance from the point charge to B is RB. As we work through the math, we will find the expression of the potential difference between 2 points of a point charge. With the same equation, and let RA goes to infinity and RB to be R, we get the following equation, which is the amount of work to move 1 coulomb of charge from infinity to R, assuming V infinity equals to 0. With this information, we can start working on our problem. We are asked to find the work that it takes to move a negative 2c charge from infinity to the assigned coordinate. We can start this problem by analyzing the distribution of each charge. Each charge has a distance r from negative 2c charge, and in this problem, all charges have the same distance from the negative 2c charge, which is 2 meters. Next, we can start finding the potential difference between the infinity and the assigned coordinate. Each charge has its own electric field, and we know that superposition holds with Coulomb's law. We can combine all electric field to find the potential difference due to multiple charges. After plugging the values, we find that the potential difference is negative 18 volts. We know that the potential is just the amount of work it takes to move 1 coulomb of charge from infinity to the coordinates. To find the amount of work to move negative 2 coulomb of charge from infinity to the coordinates, we can simply multiply the potential difference by negative 2 coulomb, which will be 36 joules.